Good evening to everyone. Welcome to the 5th live interactive session for concrete technology. I am Sedu Vinayagam, a PhD scholar in the Civil Engineering Department at IIT Madras. Okay, let's start with an overview of the concepts that were covered in the lectures for week 5. So week 5 had 3 lectures. So the first lecture, so this week 5 was about mixed design or mixed proportioning of concrete, right? So we looked at the individual components like the coarse aggregates, fine aggregates, cement, and the admixtures, chemical and mineral admixtures in the previous weeks. And in this week we were looking at how do we mix these different components together in order to get the desired properties of concrete, right? So the first lecture was about the general principles of this mixed proportioning, right? And then it also talked about the specification. So how do we specify for a given design? What are the things that we need to specify in order to get the right mix, right? So in terms of that specification, we look at different properties both at the fresh state as well as at the hardened state, right? So the fresh state properties like the workability generally defined in terms of slump or other metrics as well, like VB time or compaction factor. And then also the properties at the hardened state also, like the compressive strength, the durability, and so on, right? So those are the properties that we will be specifying in order, or the properties, the values that we will try to achieve through our mixed proportioning. And also towards the end of the first lecture, we looked at the nature of strength variation, right? So if we take a particular type of cement, particular type of aggregate, right? So we fix all the materials to the same thing, but when we make different specimens out of the same set of ingredient, like we would not always get the same strength out of it, right? So even though we take M30 grade of cement and we take a particular type of sand, particular type of aggregates, like same shape, etc., if we cast multiple specimens out of it, we will be getting different strength Why? Because of variability in different processes involved, right? So there will be variability in mixing, there will be variability in curing, and so on, right? So because of these different variations, there will be variation in the strength that is achieved as well, right? So we looked at that strength variation, and how do we use that distribution of strength variation in order to quantify the characteristic strength. That was covered in first lecture. The second lecture we looked at two specific methods. One is the IS method, the specified by the Indian standard, and other one is the British standard, which is the DOE method. And in the final lecture we looked at an example covering the two methods, IS as well as the DOE method, right? So we'll look at some problems with respect to mixed proportioning. So the first question is to calculate the target mean strength for M30 concrete as per the Indian standard, right? So to do that you will need the standard deviation value. You can take the standard deviation value to be 5. Okay, you can take a minute or two to complete it, and you can answer in the chat when you're ready. Okay, any answers? Okay, so let's see how we will solve this. So we want to find out the target mean strength, right? The strength that we will design for, right, using an M30 grade of concrete, right? So and we are given the standard deviation as 5. So the relationship that that we are using is this: Fm is equal to FCK plus 1.65 sigma, right? So in this equation, on the left hand side we have the mean strength, which is represented by Fm. So that is given by FCK, which is the characteristic strength of concrete, plus 1.65 times the standard deviation of the strength variation, right? So we said that there will be variation in the strength when we cast different specimens, right? So it is, the sigma is the variation in the strength of the different specimens that we will get out of it, right? So, and this value is given to us directly. We will find it, actually we have to find it out experimentally, but for different grades the standard gives us this standard deviation value as well. And for M30 we can take sigma as 5 MPa, right? And what does this relation tell us? So what is this characteristic strength? This characteristic strength is given is coming from the grade of the concrete, right? So when it is M30, the characteristic strength is 30 MPa, right? So what does that mean? So the characteristic strength is nothing but, so it is that value, right, which 95% of the samples will exceed, right? So if it is 30 MPa, then if you take many samples, then 95% of them will have a strength that is at least 30 MPa, right? So that value is called the characteristic strength. But we want the mean strength to be not equal to this characteristic strength, but to be higher, right? Because in the field we want to be conservative, right? So we want to be more safe. Therefore we will take some we'll design for the mean strength and not for the characteristic strength, to allow for this safety. And what is that value of the mean strength? It is FCK plus 1.65 sigma, and this 1.65 sigma is basically is how far the mean of the distribution is from the 5th percentile, assuming the distribution is Gaussian, right, or a normal distribution. So from that we get this relation. So now we want to calculate that mean strength. So we are given the grade of concrete, so from that we'll get the characteristic strength as 30 and then 1.65 times sigma, which is 5 MPa, right? So if you calculate this, then it will be 38.25 MPa. Okay, so that is the target mean strength that we will design for. Okay, any questions? Okay, so moving on to question number 2. So you are to design a concrete system with 30% fly ash in cementitious material for a 28-day target mean strength of 35 MPa. The cement, water, fine aggregate and coarse aggregate content for the control mix for the same 28 days target mean strength are 378 kg per meter cube, 200 kg per meter cube, 678 kg per meter cube and 1155 kg per meter cube respectively. The water reduction is 15 kg per meter cube for the same workability for the amount of fly ash mentioned. Assume a value of 0.3 for K factor and reduction in wet density of concrete due to the reduced water content and the introduction of fly ash in the mix as 40 kg per meter cube. And calculate the following for the trial mix with fly ash for the same workability, same MSA and same zone of sand. So the water content, cement content, fly ash content and fine aggregate content of the new mix should be determined. Okay, so basically we have all the details that we need for a control mix. What is this control mix? Control mix is without any fly ash, right? So it's just water, cement, fine and coarse aggregates. And for that control mix, we know what is the content of these 4 components. We know its strength, target mean strength, and and now what we want to find is we want to add some 30% fly ash. So because of that, there is some water reduction and also there is some wet density reduction, right? So that is the trial mix, and for that new trial mix where fly ash is added, we need to determine 4 quantities: the water content, cement content, fly ash and the fine aggregate content. Okay, so we will do this one by one. So let's just find out the water content first. So you can take a minute to calculate the water content, and when you are ready you can answer in the chat, then we'll look at the solution. Okay, shall we look at the water content for the new mix? Any answer before we look at it? Okay, so let's look at how do we find the water content of the new mix. Okay, so water content of the trial mix. So let us call that W or W prime. So how do we find out this W prime? So we know for the control mix what is the water content that is required, right? So for the control mix, it is given that the water content required is 200 kilograms per meter cube, and it is also given that the water reduction is 15 kilogram per meter cube for the same workability for the amount of fly ash mentioned, right? So it is straightforward. They have directly given us what is the reduction in the water content. So all we have to do is from the given water content for the control mix, reduce this 15 kilogram per meter cube, then we will know what is the water content for the trial mix, right? So it is W, which is the water content for the control mix, minus delta W, which is the reduction in the water content. So 200 minus 15, so it will be 185 kilogram per meter cube. Right, so that's it. So because we are given both pieces of information, the water content for the control mix and also the reduction when reduction in water content when the fly ash is added, right, for the same amount that is given in the question. So it is just a difference of the two. But why is the water content reducing? Because remember, from I think 2 weeks ago we looked at mineral admixtures and their effects. So fly ash was one of them, and we saw that adding addition of fly ash will reduce your water requirement, right? So why? Because it is spherical. These are fine particles, spherical in shape, right? So they will reduce the amount of water that you need, right? So they will reduce the porosity, and then they will also reduce the water content, right? So therefore, if you want to have the same workability, if you don't want to increase the workability, then we just have to add lesser water than earlier if we are adding fly ash, right? So that's why the water content is reducing and the new water content is 185. Okay, now for the second part is to find out the cement content of the new mix, right? So now we are replacing some of the cement with fly ash, right? So now we want to find out what will be the amount of cement that we need to add when we are adding 30% fly ash. Okay, again you can take a minute. Okay, so let's take a look at the solution. So we want to find out the new cement content now, right? So what is the information that is given to us? We are given the proportion of fly ash, or the percentage of fly ash in the total cementitious material that we want, right? So how do we write that? So if P is that is the percentage of the fly ash in the total cementitious material, then P will be equal to F over C prime plus F times 100, right? So the total cementitious content will be C prime plus F, right? So C is the new cement content that we are looking for, and C prime plus F is the total cementitious material, and the proportion and the percentage of fly ash in that will be F by C prime plus F, right, into 100 to get it as percentage, right? So from this, let us just find out what is F in terms of C prime. Okay, so if we just simplify this, then it will be P C prime plus PF is equal to 100F, right? So from this we can write 100 minus, or 100 100 minus P times F is equal to P C prime, right? So therefore F is equal to P C prime by 100 minus P, right? So this is the amount of fly ash in terms of given a certain proportion and the new cement content, right? So C prime. So this is one piece of information. We'll use this later. So the other equation that we want that we will use is W by C. Let us say the control mix is water to cement ratio is W by C. Okay, we want the same water to cement ratio to be maintained in the trial mix also. After we add the fly ash, then also this ratio should be maintained, right? So for that, let us say the new water content is W prime that we calculated earlier. So divided by the new total cement content will be what? It will be C prime plus some K times F, right? So why it is K times F? Because this K is actually the equivalence factor, right? So it is not all of the fly ash that we amount is not equivalent to the cement that it has replaced. So it is only some proportion of it, right? So in the problem that you are given, we take the K as 0.3, right? So it is only 30% of the fly ash is equivalent to the cement that it is replacing, right? So the new water to cement ratio that we will need is W prime by C prime plus KF, right? So in this let us again rewrite this. So from here we will try to find out what C prime is. Okay, so W by C times C prime plus KF is equal to W prime, right? So now here we have two unknowns actually. So W prime we know, W by C also we know, K also we know. C prime and F both are unknowns, but we already have found an equation for F in terms of C prime, right? So we can use that here to find out what C prime is. So I'm just going to replace this equation that we found earlier into this term here. So we will have W by C times C prime plus K into F is replaced by that. So K P C prime by 100 minus P, okay, equal to W prime. Okay, so let's go here. So if we take C prime as a common from these two terms on the left hand side, so we will have W by C. So actually this W by C is common for both of these. Right? So here also it is common. So it is W by C times C prime into 1 plus Kp by 100 minus P. So this is equal to W prime. Right, so I have just taken C prime common. Okay, next if we just write W by C times C prime, so into, I'm just going to take 100 minus P, multiply 1 by 100 minus P and divide by 100 minus P, so then we'll get 100 minus P plus Kp, and then taking the denominator to the right hand side, it will become 100 minus P times W prime. Right, so we are almost done. So now we can find what C prime is. So C prime is equal to 100 minus P times W prime. Right, so divided by W by C into, so 100 minus P plus Kp, so it can be written as 100 minus one minus K into P. Right, so if we take P common, so it will be minus 1 plus K, we are taking another minus out, so it will be 100 minus 1 minus K into P. Right, so now we have an equation for the new cement content, right, C prime. So on the right hand side, everything is known. We know P is the percentage of the fly ash, and then W prime is the new water content, W by C is the old water to cement ratio in the control mix, and K is the K factor value, which is also given as 0.3. right, so we have all the information that we need to find out C prime. Right, now we just need to substitute the values. So C prime is nothing but 100 minus P. So here P is in terms of percentage, not proportion, because we multiplied by 100 when finding this. Right, so in the question P is given as 0.3 or 30%. Right, so we just have to use 30 for that. And the new water content, we already found that as a part of the previous question, it is 185. Right, so into 185, so divided by the water to cement ratio we need, so that is it's not given directly, but we know the water content and the cement content. Right, so the cement is 378 kilogram per meter cube and water is 200 for the control mix. So it is 378 by 200, that is the water to cement ratio, 378 by 200 into 100 minus, so K is 0.3, so 1 minus that is 0.7, right, times 30. Right, so if you simplify this, you will find out what the new cement content is. Okay, and that will come out to be approximately, you can say that is 310 kilograms per meter cube. Okay, so that's how we find the new cement content. So you need not derive this every time, so you can remember this as the final equation. So where we need the proportion that we are adding for the fly ash, and the new water content, the old water to cement ratio, and the equivalent K factor. Right, so with that we can find out what is the new cement content. Okay, any questions? How do you find the new cement content? Okay, right, so the third question is to find the fly ash content of the new mix. Right, so again already we got the equation for that, right? So we first derived that. So the fly ash content of the new mix in terms of the new cement content, right? So we know that. So this is the equation that we need, right? So in this, again, we know all the information that is necessary, right? So P is 30 times C prime, we just now found out it is 310 kilogram per meter cube. So that is 310 divided by 100 minus P30, right? So again, if you calculate that, the value will come out as again approximately 133 kilograms per meter cube, right? So this is the fly ash content for the in the new mix, right? Any questions? So we are just using the equation that we derived earlier. Okay, and then the final quantity that you want to determine is the fine aggregate content. Okay, okay, how do we determine the fine aggregate content now? So to do that, we will need to know the total wet density of the concrete, right? So first, for the wet density for the control mix, okay, so what is that for the control mix? It is 378 plus 200 plus 678 plus 1155, right? So those are the 4 individual components, right? Therefore we can add those individual components unit volumes, right? So 378, 200, 678 and 1155. 378 plus 200 plus 678 plus 1155. So that is the old or the control mixes wet density, which is 2411, right, kilogram per meter cubed, right? Now what we are also told that because we are adding fly ash, right, so the trial mixes wet density will come down, and that reduction in the wet density is also given as 40 kilogram per meter cube, right? So wet density for the trial mix that we are going to do is 2411 minus 40, right? So because there is a reduction, it is 40 kilogram per meter cube. So the new density is 2371. Okay, so now we need to find out the fly ash or the fine aggregate content, right? So for that we need to know what is the proportion that was there in the control mix, right? So to do that, how do we get it? So earlier we know that there is 678 kilogram per meter cube, right? And then the coarse aggregate is 1155, right? So we can find out the proportion of the fly ash in the control mix, right? Proportion of not fly ash, fine aggregate Fa in control mix. So that is 678 divided by the total aggregate content is 678 plus 1155, right? So that is around 0.37 approximately, right? So 37% of the aggregate volume is taken up by the fine aggregate alone, right? And the rest of it, 63%, is by the coarse aggregate. This is in the control mix, and the same proportion it will be there in the new mix as well, right? So so for that we so if we know the total aggregate content, from that we will be able to find out the fine aggregate content, right? So therefore so the wet density for the new or the trial mix is 2371 kilograms, right? So this is actually equal to what is the new water content? New water content is 185 plus 310 is the new cement content, right? Plus whatever is remaining, that is taken up, plus we have fly ash as well, which is 133, right, plus whatever is the aggregate content, so W AGG. So right, so this will give us the total wet density, right? So from this we will be able to find out what is the density for the aggregate. So that will just be, you take everything else the other side, so 2371 minus 185 minus 310 minus 133, so that will give us the total aggregate content, which will be 1743 kilogram per meter cube, right? So knowing the total aggregate content, we will be able to find out the fine aggregate content in the trial mix. So that will be in the same proportion as earlier, which is 37%. So it is 0.37 times this total aggregate content. So that is approximately 645 kilograms per meter cubed. Okay, so that is the final one that we wanted to determine, the fine aggregate content. Okay, any questions? Okay, so first we found out what is the new water content of the trial mix, so which is the control mix is water content minus the reduction, right, so which came out to be 185. Then we derived what is the fly ash content in terms of the new cement content, and then we also found out what is the new cement content, right? So that was 310 kilogram per meter cube, and the fly ash content was 133 kilogram per meter cube. Then for finding the fine aggregate content in the new mix, first we found out what is the total aggregate content. So to do that, we use the wet density of the trial mix. So wet density of the trial mix was given as 40 kilogram per meter cube, lesser than that for the control mix, right? So using that and also the other three components, water, cement and fly ash, we found out the wet aggregate content, which was 1743. And then using the proportion of the fine aggregate in the total aggregate content from the control mix, we found out what is the fine aggregate content in the new trial mix. Okay, there are no questions. We'll move on to the next one. So the next one, we have 4 statements here, and then we want to find out which of these statements are true. So the first statement is durability requirements are defined in terms of the minimum cement content, maximum water to cement ratio, and the minimum grade of concrete. Second statement is that angular aggregates have best packing density among all the aggregates. And statement 3 is strength of concrete is mainly governed by the water to cement ratio. And statement 4 is fresh cement properties mainly depend on the water content in the concrete mix. So which of these statements are true? The options are 2, 3, 4, 1, 2, 3, 1, 3, 4 and 1, 2, 4. Okay, let's take a look at the answer now. The right answer is option C, 1, 3 and 4. Right, so the first statement says that the durability requirements are defined in terms of the minimum cement content, maximum water to cement ratio and the minimum grade of concrete. Right, so it is correct. All these three quantities are used to define or to specify the durability requirement, right? So we don't have a direct measure of the durability, right? So therefore we define the to get the desired durability result, So we make sure that these quantities are satisfying, or we make the specification in terms of these quantities, which is what is the minimum amount of cement, and the maximum water to cement ratio, and the minimum grade that should be used. Therefore the desired durability will be obtained, right? So that is true. That is how the codes specify the durability requirements. So statement 2 is that angular aggregates have the best packing density among all the aggregates, right? So that is false. So we know that angular aggregates actually increase the porosity, right? So it is the spherical aggregates which provides the best packing density, right? And therefore with increasing angularity you will have more porosity, and then the packing density will come down because of that, right? So therefore statement 2 is incorrect. Statement 3 is strength of the concrete is mainly governed by the water to cement ratio. Again we have seen this. The water to cement ratio is one of the major factors that govern the strength, right? So we try to keep this water to cement ratio as low as possible, right? So when you have a higher water to cement ratio, there will be more water content, right? And that excess water will actually lead to higher porosity later, and therefore a reduced strength. Therefore there is a clear relation between the water to cement ratio and the strength, and therefore statement 3 is correct. And statement 4 is fresh concrete properties are mainly dependent upon the water content in the concrete mix. Again this is also true. What is the fresh concrete properties? So some fresh concrete properties include like the workability, again, so those depend upon the water content. So you have lower water content, you will have lower workability, higher water content, higher workability, and so on, right? So therefore it is dependent. The water content will affect the properties of the concrete at the fresh state, right? So therefore statement 4 is also correct. So out of the 4, 1, 2 and 4 are correct, and 3 is incorrect. So the right option is option 3, 1, 3, 4. Okay, moving on to question number 4 is which of the following statement is incorrect, right? So again we have 4. Higher VB time shows lower workability. Option B is higher slump shows higher workability. Option C is higher compacting factor shows higher workability, and option D is none of the above. Okay, so we have 4 different statements related to workability. So let's look at the answer. So the answer is none of the above, which means that all the 3 statements A, B and C are correct. Okay, so all these 3 different quantities are used to measure workability, and the relationship that is defined here is also correct. So in terms of VB time, so higher is the time means lower is the workability, right? So that is true. And then in terms of slump, it is the reduction in the height, right? So that when there is a higher slump, right, which means that there will be higher workability as well. And then this compacting factor is when this compacting factor, it will be between 0 and 1. So when it is higher, like when it is closer to 1, it means that there is more workability. So you need to do lesser compaction in order to compact it, right? So therefore your concrete is more workable, right? So higher is the compacting factor, higher is the workability. So the trend is correct in all the 3 statements. Therefore none of them is incorrect. Okay, so question number 5 is again a design problem as per the British DOE method. So we have to design using an M30 grade of concrete, and we have to assume that the maximum size of the aggregates is 20 millimeters and the slump is 25 millimeters, and we are given a certain set of charts and tables that we can use. And the 28-day compressive strength for 0.5 water to cement ratio is 49 MPa, right, for this given grade of concrete and the aggregates and the slump requirement, right? So when we use a water to cement ratio of 0.5, we get a 28-day strength of 49 MPa, right? And then the aggregates, the coarse aggregates are to be crushed, and we are also assuming the specific gravity of aggregate as 2.7. Now the maximum allowable water to cement and the minimum cement content from a durability point of view are 0.65 and 260 kilogram per meter cube respectively, right? So we are given the durability requirements in terms of the maximum water to cement and the minimum cement content, and the fineness of the fine aggregates is 40% passing through 600 micron sieve, and the wet density of the concrete is 2490, right? So we have been given these information, and what we want to find out is the target mean strength, assuming that the standard deviation of the strength is 5 MPa, the water to cement ratio that will yield this this target mean strength, and then the free water content that should be used in the mix based on the given slump requirement, which is 25 mm, and then the content of the fine aggregate to be used in the mix, right? So we are given the water content for different slump, and then the type of aggregates, and also the proportion of fine aggregates for different slump requirements based on the water to cement ratio, and also the compressive strength, the relationship between the compressive strength and also the water to cement ratio, right? So let's work out each one. So first we want to find out the target mean strength, right? So this, irrespective of the method, whether it is IS method or the DOE method, the method of finding the target mean strength remains the same, so as we saw earlier. So the target mean strength is given by Fm is equal to Fck plus 1.65 sigma, right? And what so to find the target mean strength, we need to know the characteristic strength and the standard deviation. Both are known to us. The characteristic strength can be obtained knowing the grade of concrete, right? So if it is M30, the characteristic strength is 30 MPa, right? And also the standard deviation is given to us, or it is it is given as 5 MPa, right? So using these two information, we will be able to find the target mean strength. So it is 30 plus 1.65 times 5, which is 38.25 MPa, right? So that is the target mean strength that we should design for, okay? So the second one that we want to determine is the water to cement ratio that will give us this target mean strength that we have calculated. So to achieve 38.25 MPa mean strength, what should be the water to cement ratio that we should use? So how do we find that? So if you look at the information given to us, we know the relationship between compressive strength and the water to cement ratio, but there are a series of curves that are given to us, right? So which one of these different curves do we choose? So to do that, what do we and why are we different curves? Is because there are differences in the type of aggregates, right? There are differences in the type of aggregate in the method used for mixing, curing, etc., right? So therefore there will be different there will be variations seen in this relationship. So we want to find out for our condition which is the best which is the curve that will best define the relation between the strength and the water to cement ratio. So to determine that, we use we cast a specimen for a 0.5 water to cement ratio, and then find out what is its strength after 28 days, right? And this is already given to us, like for a 0.5 water to cement ratio, the strength that we get after 28 days is 49 MPa, right? So we can use this piece of information to determine which curve will be best suitable for our condition, right? So for a 0.5 water to cement ratio, so we can find out from the different curves will give us different compressive strength. So the curve which gives our compressive strength of 49 MPa, okay, that is given here highlighted with this red underline. So this curve is the one that best represents our condition, right? So this is the curve that we should be looking at, right? So that is for us. Okay, now how do we determine the water content or the water to cement ratio for our target mean strength? Now, knowing that this is the curve that we will be using, and also the target mean strength which we have calculated as 38.25, right? So for 38.25, if you find out from on this curve what is the water to cement ratio that will give that is somewhere here around 0.58 or 0.59, right? So we can approximately take it as 0.6, okay? that is how we determine the water to cement ratio that is to be used, right? So the water to cement ratio, required water to cement ratio for FM, right? So that is 0.6, right? Any question how we obtained this water to cement ratio? Okay. So we found out the water to cement ratio that will give us 38.25 MPa of mean strength, right? So the third quantity that we want to find out is what is the water content that we should add, right, based on the slump requirement, right? So to attain slump of 25 mm, what will be the water content that is necessary, right? So to do that we need to use this particular table, right? So we know slump requirement, and we also know the type of aggregate that we are using. So based on that we can find out the water content, right? So the slump requirement is 25 mm, and the type of aggregate that we are using is crushed aggregate with the maximum size of the aggregate of 20 mm, right? So if you look at, there are different slump values given. So 0 to 10 mm, 10 to 30, 30 to 60, and 60 to 180. So ours is 25 mm, right? So which falls in the 10 to 30 mm range, right? So we need to look at the second column here, and the based on the type of aggregate we are using 20 mm MSA, right? So, and also crushed. So for 20 MSA and crushed and to 10 to 30 mm slump, so the water requirement is 190 kilogram per meter cube, right? So that's how we determine the water content. So water content for 25 mm slump is 190 kilograms per meter cube. Okay, any questions on how we obtain the water content? Okay. So the final one quantity that we want to determine is the content of the fine aggregate to be used in the mix, right? So we want to find out the fine aggregate content, but before we find that, we also need to know what is the cement content. So therefore we can find out this fine aggregate content. So how do we find the cement content? So we know the water to cement ratio, which is 0.6, and we also know the water content for the slump requirement, which is 190. So using those two we can find out the cement content, right? So C is equal to W by the water to cement ratio, which is 0.6, right? So it will be 190 by 0.6. So that will give you the cement content, which will be around 370 kilogram per meter cubed, right? So using the water content calculated and also the water to cement ratio found out, we get the cement content. So now we want to find out what is the total aggregate content. So to find out the total aggregate content, so we have the wet density, and we also know the water content and cement content. So using these three information, we will be able to find out what is the total aggregate content. So let us say, so wet density is equal to the water content plus the cement content plus the aggregate content. So I am calling that as WAGG. Okay, so the wet density is given as 2490 kilogram per meter cube, right? So 2490 equal to 190 plus 317 plus WAGG. Okay, from this we will be able to find out what is the total aggregate content, which is 2490 minus 190 minus 317. Okay, so that is 1983 kilograms per meter cube. Okay, we have found out the total aggregate content, not the fine aggregate content yet, right? So what the question asks us to find what is the fine aggregate content in the mix. Okay, so how do we find out the fine aggregate content? So for that we'll use the other chart that is given to us. So here we know what is the proportion of fine aggregate given water cement ratio, for a given water to cement ratio for different slump requirements. Okay, so our slump is 25 mm, right? So it is in this 10 to 30 mm range. So we'll be looking at this graph, and the water to cement ratio that we are using is 0.6, right? And for this again we have a series of relations given to us, and therefore we need to use the other information that is given to us, which is the fineness of the fine aggregate, right? So which is 40% of the fine aggregates are passing through 600 micron sieve. Okay, so based on that, if you look at it, it is this particular curve uh, which is what we need to be looking at. So this numbers here is showing us the fineness of the fine aggregate, right? So 40. So for 0.6 water to cement ratio on this line, if you look at it, the proportion of fine aggregate is approximately, we can take it as 0.45. Okay, so that is the proportion of fine aggregate in the total aggregate content. Okay, proportion of fine aggregate in WAGG, so which is 0.45. okay, so what is the fine aggregate content then? So it will be nothing but 0.45, this proportion times the total aggregate content, right? So which is 0.45 times 1983, which is the total aggregate content, right? So that will come out to be approximately 892 kilograms per meter cubed. Okay, so we found out what is the target mean strength, we found out what is the water to cement ratio required, we found out also what is the water content required, and also the fine aggregate content, right? So any questions? How do we use the DOE method? Okay, so first we use the relation between the target mean strength and the characteristic strength, right? So we found out, so we know the grade of concrete, we know the standard deviation, using that we find out the target mean strength. Then we found out the water to cement required from water to cement required for the target mean strength, right? So using the relationship between the compressive strength and the water to cement ratio. So we took a trial mix of for 0.5 water to cement ratio, and we measured its characteristic strength after 28 days, and then we found out which curve to be chosen. And once we chose the curve, we found out for the target mean strength what is the water to cement ratio that is required, right? So that is the second step. Third, we found out the water to cement content based on the slump requirement and also the type of aggregate that we are using, right? So for the given slump requirement and the type of aggregate, which is 20 mm MSA and crushed aggregate, so we found out what is the water content required, right? So that is from the table directly. And then using the water to cement ratio and the water content, we found out what is the cement requirement or the cement content, right? So it is water content by the water to cement ratio. And then we used the wet density information and the water content and the cement content calculator to find out the total aggregate content in the mix, right? So it is the wet density minus water content minus the cement content, which is 1983 kilogram per meter cube. And so we need, but what we are really interested in here is the fine aggregate content. So to find the fine aggregate, we need to know what is the proportion in this total aggregate that belongs to the fine aggregate. So to do that, we use the other chart, so where the proportion of the fine aggregate is given in terms of the for the different water to cement ratios, and also there are different equations for different fineness, right? So for the given fineness, which was 40, so we found out for the water to cement ratio of 0.6 that the proportion is 0.45, right? For a slump requirement, between 10 and 30, and using that proportion and the total aggregate content calculated, we found out the total fine aggregate content. Okay, so if there is no question, we'll move on to the next one. Here again another design problem which is using the IS method now. So here we want to design that M35 grade of concrete using IS method, assuming that the water to cement ratio is 0.45, it is directly given to us, and the percentage of the fine aggregate to that of the total aggregate is 35% by volume, assuming the unit weights of cement, water, coarse aggregate and fine aggregate to be 3150, 1000, 2600 and 2700 kilogram per meter cube, and also a slump range of 75 to 80 mm, the maximum size of aggregate as 20 mm, and we are also given a table that gives us what should be the water content for a given slump range, and also the change in slump from this table. For every 50 mm increase, we need to increase the water content by 3%. Okay, so this is the information given to us. We want to determine what is the water content required for the mix, the volume fraction of the total aggregate in the concrete, the percentage of coarse aggregate to that of the total aggregate by volume, and the total unit weight of concrete. Okay, so let's do it one by one. So first let us find out what is the water content that is required, right? So we are given a table which shows what is the water content required for the type of aggregate that we are using, which is angular crushed aggregate, and also for a slump range of 25 to 30 mm. Okay, so that table is given here, right? So for different sizes of aggregate of angular crushed type, so the water content is given here. Okay, so for so our problem is saying that we are using an MSA of 20 mm, right? So for 20 mm MSA, the maximum water content is 186. Okay, so for 20 mm MSA, water content is 186 kilogram per meter cube. Okay, but this is not enough. Why? Because the value that is given here in the table is for a slump range of 25 to 30 mm, right? But the slump range that we are working with is 75 to 80 mm, right? So we need to adjust the water content given in this table. And how do we adjust that? It tells us that for every 50 mm increase in this slump, right, we need to increase the water content by 3%. Okay, so our slump requirement actually is 50 mm higher than the given one, right? So 25 to 30, so ours is 75 to 80, so it is 50 mm increase. So therefore we need to increase the water content by 3%. Okay, so this is actually also 20 mm MSA and 25 to 30 mm slump is this, right? So for 75 to 80 mm slump, W will be actually, so it needs to be increased by 3%, so it will be 1.03 times the water content that is given to us in the table, right? So it is 1.03 into 186, and that will be 192 kilograms per meter cubed, right? So that is the water content that we need for the given slump requirement. Okay, 192 kilograms. So that is for the first part. So the second question is to find out the volume fraction of the total aggregate in the concrete. Okay, so how do we find out the volume fraction of the total aggregate in the concrete? So for that we need to know, so if we know the total volume, if we take it as 1, right, we need to subtract the volume fractions of the other components, so which is water, cement, to find out what is the volume fraction of the total aggregate. Okay, so how do we do that? So the total fraction is 1. Okay, this is equal to the volume fraction of water. So let me write a WF. So this represents the fraction of volume taken by water, and then WC for cement, and then W A for aggregate. Okay, so this is equal to, so how do you find out the volume fraction for water? So it is this water content, which is 192, divided by its unit volume, which is 1000 kilogram per meter cube, right? So that is its volume fraction. And then for cement, so we need to know what is the cement content also, right? So we need to find out the cement content. So how do you find out that? We are given the water to cement ratio, right? So that is given as 0.45. so we also know the water requirement, so based on that we can find out the cement content. So cement content is capital C is equal to the water content divided by water to cement ratio, W by C. So water content is 192 kilograms per meter cube, and the water to cement ratio is 0.45, right? So this will give us approximately 427 kilograms per meter cubed. Okay, that is the cement content that we need. So to find out the volume fraction for the cement, so it will be 427 divided by the unit volume, which is 3150, right? So we are given that in the question, 3150 for cement unit weight. And then whatever is remaining, okay, let us call that as X. So this X is the volume fraction for the total aggregate in the concrete, right? So that is what we want to find out. Let's say that is X. Okay, so from this we will be able to find out what X is. So X is nothing but the volume fraction of total aggregate. So that is 1 minus 192 by 1000 minus 427 by 3150, right? If you calculate it, it will be 0.67, right? So 67% of the volume is taken up by the aggregates in the concrete. Okay, so that is for the second part, the volume fraction of total aggregate. The third question is to find out the percentage of the coarse aggregate to that of the total aggregate by volume, right? So here we are not looking at the concrete as a whole, we are only looking at the total aggregate content, and then out of that total aggregate content, what is the percentage occupied by the coarse aggregate alone, right? So this is straightforward, because we are directly given that the percentage occupied by the fine aggregate in the total aggregate is 35% by volume, right? And there is only fine aggregate and coarse aggregate, so therefore the rest of the volume is taken up by the coarse aggregate. Okay, so percentage of coarse aggregate Ca in total aggregate, so that is nothing but 100 minus 35, which is 65%, right? So this we can directly find out, because the fine aggregate proportion or the percentage in the total aggregate content is given to us, right? So it is 35. So for coarse aggregate, it is nothing but 100 minus 35. So that is for the third part. And the final question is about finding out the total unit weight of concrete, right? So we need to find out the unit weight for the concrete as a whole. We know for each individual quantities, so we want to find out for the concrete as a whole. So to do that, we already know what is the unit weight for or the weight in the unit volume for contributed by water as well as by cement, right? So it is 192 by water and 427 from the cement, right? So we need to find out for the other two components, which is the fine aggregates and the coarse aggregates. Okay, so how do we find out that? So again, we will use the same equation where we found out the from which we found out the unit or the volume fraction. So 1, which is the total fraction, is equal to the fraction contributed by water, which is 1000, plus 427 by 3150. This is the contribution from cement. And then for the fine aggregate, what we will do, it is 1 by 0.35 times whatever is the fine aggregate content divided by the unit weight of it is 2700. Okay, right? So why do we divide by 35? Because fine aggregate is only occupying 35% of the volume, right? So the volume fraction for the fine aggregate is Fa by 2700, but it is only 35% of the total aggregate volume. So we divide by 0.35 so that this this represents the total volume occupied by the aggregates in the concrete system. Okay, from this we can find out what is the fine aggregate content. So Fa will be nothing but 1 minus 192 by 1000 plus 427 by 3150. This whole thing will be multiplied by 0.35 multiplied by 2700, right? So this will give us, if we calculate it, this will give us the total quantity of the fine aggregates, which will be approximately 636 kilograms per meter cubed. Okay, so in a similar fashion we can able to find out the coarse aggregate content as well. So which is just one component, which is only the last component that is missing, right? So we know water, we know for cement, now we know for fine aggregate as well. So fine aggregate we calculated it as 636. So the remaining component is only the coarse aggregate, and then its unit weight is 2600 kilogram per meter cubed, right? So from this relation, so the coarse aggregate content will be nothing but 1 minus the contribution from the other three, multiplied by 2600. Okay, so this will give us what is the coarse aggregate content, so which will be 1136 kilograms per meter cube, right? So we found out the water content, cement content, the fine aggregate content, and the coarse aggregate content, but what we wanted to find is the total unit weight, right? So it will be nothing but the sum of all the four components. So total unit weight of concrete is equal to, so water content, which is 192 kilograms per meter cube, plus cement 427, for fine aggregate 636, and then for coarse aggregate it is 1136. So if we sum all those up, it will be 2436 kilograms per meter cubed. All right, so that's how we find out the total unit weight of concrete, right? So what did we do? So this is the IS method. So first we started with finding out what is the water content in the mix, right? So to do that we used this particular information. So where we are given for different the nominal maximum size, what is the maximum water content that we can have, right? So this is for a particular type of aggregate, so it will vary for different aggregate types. So we are given for angular crushed aggregate, right? So for 20 mm MSA for angular crushed aggregate, the maximum water content is 186 kilograms per meter cube. Okay, so that we found out, but that is for a particular slump range, which is 25 to 30 mm, right? So if our slump range is higher than this, then for every 50 mm higher slump range, we have to increase the water content given in the table by 3%. So our slump range was 75 to 80, which is 50 mm higher. So we increased this 186 by 3%. So right, so it is 1.03 times of that, so which gave us 192 kilogram per meter cube, which was the first step, right? So then we found out the cement content. So the water to cement ratio was given to us as 0.45. So the water content, which is 192 by the water to cement ratio, which gave us the cement content of 427 kilogram per meter cube. Then we were interested in finding the total or the volume fraction of the total aggregate in the concrete. So how did we find that? So the total volume fraction is 1, right? So this is composed of the volume contributed by the water, cement and the aggregates, right? So the volume fraction from water is its content divided by its unit weight, water's unit weight, plus cement content by cement unit weight, plus the volume fraction of the aggregate, right? So using that we found out what is the volume fraction of aggregate, and it came out to be 0.67. so 67% of the volume is occupied by the aggregate in the concrete mixture. Then the question was about finding out the percentage of coarse aggregate to that of the total aggregate, right? So this was straightforward because the percentage of the fine aggregate in the total aggregate is given to us as 35% by volume. So the rest 65% should be coarse aggregate, right? So therefore it was 100 minus 35. So that was straightforward. And the final question was to find out the total unit weight of concrete. So to find this out, we need the unit weight of the individual components, which is water, cement and the fine and the coarse aggregates. So we already found out the unit weights for the water and also cement, which is 192 and 427. So we needed the unit or the content of fine aggregates and the coarse aggregate. So we again used the volume fraction, the equation that we used for finding out the volume fraction of aggregates. So the total volume fraction is 1. So the contribution from water is 192 by 1000, contribution from cement 427 by 3150, and then for the aggregate, so we took one aggregate at a time, so which is fine aggregate first. So the volume of fine aggregates is the weight of fine aggregates divided by its unit weight 2700, but this is representing only 35% of the aggregates volume. So we divided by 35.35 to get the volume for the total aggregates, right? So using that we found out the volume of the content of fine aggregate as 636 kilogram per meter cube. And then again finally we found out the content of the coarse aggregate using the same relationship. So we know for water, cement and fine aggregate now, so the only remaining component is coarse aggregate. So we found out for coarse aggregate it is 1136 kilogram. So now knowing all the individual components unit weight, so we just sum them up to get the total unit weight of concrete, which came out as 2436 kilograms per meter cube. Okay, so next we'll move on to question number 7. Okay, so question number 7 is, which of the following is more critical towards the durability of a concrete system? So option the two things are porosity and permeability. So the options are only porosity, only permeability, both porosity and permeability. Option D is neither porosity nor permeability. Okay, so we are talking about durability of concrete. So porosity as well as permeability are related, right? So if you have more porosity, then your permeability will also increase, right? So what is the difference between the two? One is porosity is how much is related to how much voids you have in the total volume, right? Whereas permeability is about the interconnectedness of these different pores, right? So if you have all these different pores that you have connected together, then you will have a higher permeability. So it is about how quickly or how easily a fluid can flow through the pores in your system. So that is what will determine the permeability of the system, right? So now porosity is not necessarily a bad thing for durability unless they are interconnected, right? Why? Because so the durability we are talking about the external effects, right? That is going to affect the long term properties or the long term performance of the concrete system. So for this external agent should penetrate your system, right? So that will happen when you have higher permeability. So when you have higher permeability, so for example water containing higher chlorine content, so that can enter your system and then corrode the reinforcements, right? So this is possible when you have higher permeability, right? Therefore permeability will affect is more critical for durability, but porosity by itself is not necessarily going to affect the durability, because let's say you have more pores but these are not really connected together. In that case it is not going to affect the durability, because the external factors may not be able to reach your inside of the concrete system, right? So porosity by itself is not going to affect the durability, but there are other effects, such as reduction in the strength when there is higher porosity, right? Because the pore spaces are not really going to contribute to the strength of the concrete, right? So when you have more pores, you will have lesser strength. But here we are only talking about durability, therefore it is only the permeability which is more critical and not porosity by itself, right? Therefore the correct option is B2, which is permeability alone. Okay. So question 8, for better quality control the standard deviation should be, options are high, option A is high, option B is low. Can we have an answer? So what do you think? Should the standard deviation be higher or lower to have a better quality control? So this is related to the standard deviation of the strength variation that we saw earlier. Okay, any answer? Is it better if we have higher standard deviation, or is it better if we have a lower standard deviation in the strength variation? Okay, so let's take a look at the answer now. So the right answer is option B, low, right? So when you have lesser standard deviation, what does it mean? You have lesser variability, right? So the more repetitions, when you are making more repetitions, so every time you are going to get more or less the same strength, right? So that's what lesser standard deviation will give you, right? Because there is no larger range of variation that you are seeing. So that is better, because what you design for, whatever you are going to place in the field, it's going to be you can be more confident that it will be more closer to what you are designing for, because the strength variation is much lower when the standard deviation is low, right? Therefore a lower standard deviation is desirable for higher quality control. Okay, so question 9, it's about characteristic strength. So the statement is, characteristic strength means 50% of the samples would exhibit a strength greater than or equal to FCK. So is this statement true or false? Okay, so this is a false statement. Why? Because by definition, the characteristic strength is that value, uh, so which is exceeded by 95% of the samples, right? So it is not at 50%. It is 95% of the samples which would exhibit a strength that is greater than that value, right? FCK, right? So that is the characteristic strength value. So why? Because we have a distribution of the strength which follows a Gaussian distribution or a normal distribution, and then so this FCK is nothing but the fifth percentile of this Gaussian distribution, right? So what does fifth percentile means? It means 5% of the values is lower than that, and in other way it is 95% of the samples or 95% of the values are higher than that, right? So it is that particular value is taken as the FCK, and that is what we define it as the characteristic strength. Therefore this statement is false, right? So this is nothing but the median of the distribution, so that is not the characteristic strength, so it is false. So question 10 is about what is the objective of doing the mix design. So concrete mix design is intended to achieve specified characteristic strength, achieve required workability, achieve impermeability, and both A and B. Okay, so the purpose of mixed design is to achieve the specified characteristic strength, and so we looked at earlier, right? So when we looked at the overview, we said that in the mixed design or the mixed proportioning, we give the specification in terms of the properties related to both the fresh and the hardened state of the concrete. And we looked at one of the properties that we look at in the fresh state is the workability, right? So we do the mixed proportioning to have certain workability, to meet certain workability requirement, because in the field we have to mix it and then place the cement, right? So for that we need a desired level of workability, right? So or sometimes we will need to pump the concrete, right? So for that a certain level of workability is needed, right? So our mix proportion or the mix design should give us that required workability, right? So that is one purpose. The other is once this concrete sets, it hardens, so it will gain strength, and for we need to achieve a specified characteristic strength, right? So therefore the strength that we are designing for, that should be achieved, right? So to handle the load, therefore to achieve the specified characteristic strength is also one of the purpose, right? But to achieve impermeability is not a direct intention of the mix design itself, right? So it is not a direct purpose, so it's only options A and B, so which is given in option D, both A and B. So the right option is D. Okay, so question 11 is again on workability. So what are the factors that affect workability? So we have workability of concrete depends on water content, aggregate shape and size, mix proportion, and all the above. Okay, so we already looked at these three components in this week as well as in the previous week as well, when we looked at aggregates. So we know that water content will increase, will affect workability, right? So higher water content will give higher workability, right? And option B is aggregate shape and size. Again, both of these will affect workability. So different aggregates will provide you with different workability, right? So for example, spherical aggregates will provide you with higher workability than angular aggregates, right? So as well as the size as well affects the workability. The third is mixed proportion. Yeah, again mixed proportion will again affect. So in the mixed proportion is again we determine what should be the amount or the proportion of the water or the water content, and also the aggregate content and the cement content, right? So the proportion will also affect the workability. So all the three factors will influence workability, and therefore the right option is option D. Okay, question 12. So it's we are given two statements. So the first one is improving workability by increasing water content should be avoided as far as possible. And the second one is higher water content results in shrinkage of concrete. So the options are both A and R are true, and R is the correct explanation of A. Second option is both A and R are true, but R is not the correct explanation of A. Option C is A is true, but R is false, and option D is A is false, but R is true. Right? So we'll look at first whether the individual statements by themselves are true or false. So statement A is improving workability by increasing water content should be avoided as far as possible. So this is true. Why? Because we already saw that increasing the water content will increase the workability, right? But it is not desirable to increase the water content too much. Why? Because while higher workability is okay, but increasing the water content too much will reduce your strength, right? We know that W by C ratio affects your strength, right? So for a given cement content, when you add more and more water, it will become more workable, but your W by C ratio will also increase, right? So when your W by C ratio increases, your strength will be affected, right? But it will reduce. So why is that happening? Because when you have too much excess water that is added, that will finally lead to higher porosity, and we already saw that higher porosity will lead to a lower strength, right? Therefore this is not desirable, right? So statement A is correct. Statement R is saying a higher water content results in shrinkage of concrete. So this is not true. When you have higher water content, it will not lead to shrinkage in the concrete, right? So you will have enough water that will be there for the hydration process, right? So that it will not lead to shrinkage. Because of higher water content, you will not see shrinkage in the concrete, right? So it is a false statement. So therefore the right option is option C, that A is true but R is false. Okay, right option is C. So question 13 is again an assertion and reasoning question. So statement A is dense concrete is generally durable. Statement R is pores on dense concrete are small, right? So let's look at each of them. So statement A, dense concrete is generally durable, which is correct, right? So when you have denser concrete, the permeability will be lower, right? And therefore we already saw that permeability is one of the is more critical for that affects the durability of concrete, right? So when you have lesser permeability, there will be the durability will be higher, right? And then R says pores on dense concrete are small. This is also true. When you have dense concrete, so when you have higher density, the pores the amount of pores that you will have will be lesser, right? So that's why it is more dense, right? So because we have lesser air content now, right? So your density will increase, and that is because of there is lesser pores now remaining, right? So therefore R is also true. But then when both statements are true, we have to pick one between A and B. So that is whether R is a correct explanation of A or not, right? So but R is a correct explanation of A as well. So when you have a lesser amount of pores, your permeability will be smaller, right? So I already told this, right? So when you have higher porosity, your permeability will also be more, like porosity and the permeability are related, right? So when you have lesser porosity, your permeability will also be lower, and that will increase your durability, right? So therefore R is a correct explanation for A. So the right option is option A. Both A and R are true, and R is the correct explanation of A, right? So option A is the right answer. Okay, so that concludes the session for week 5. Okay, so we will conclude the session here, and then we'll meet again next week in the same time.
you.
Thank you for attending.